Yes, hey, welcome back. And today let's continue with our sorting series. And today I'll show you another way to sort your given array. And yeah, it is a bit complex, but it is a fun way to do. So let's directly get on with it. And yeah, it will tell us the unique property of binary search tree is that whenever you do an in-order traversal for binary search tree, your output will always be sorted. And this algorithm will relies on that fact. So what we can do is when we are given an array, what we'll do is we will directly create a binary search tree itself of the given array and then directly do an in-order traversal. Yeah, again, it's the explanation is pretty straightforward. Like what we have to do is pretty straightforward. But yeah, for that first we have to create the node and then create the trees and all. That might seem a bit daunting to new people, but hey, this is just learn it once. And if you learn it once, then you can just store it in your mind like hash map or dictionary or something. And whenever you want it, you can just retrieve it. So yes, I'll directly get on with it. So you have to have a class node because every tree will have what? Just think about it. Every tree will have a node, and so now yeah, this is the like we have to initialize some things for nodes. So yeah, let us initialize it. Yeah, the only thing you have to put inside each node is the data. So you'll take only data as the input. So yeah, self self dot data is data, and you will have a left node and a right node. So yeah, but yeah, one thing about binary search trees is that generally it does not allow duplicates because the ordering might get messed up or something. So like, but our array can contain duplicates, right? So what we can do is rather than storing duplicates as a separate node, we will store another property inside node itself. Let us call it uh, node count. We'll call it, and let us set it one. And the main task of this is to keep track of how many times a certain specific node has been repeated. For example, if you have three files, then rather than creating three new nodes for file, we'll just keep another value over there and call it as node count, and we'll increase the count by one on each iteration. So otherwise, we'll have five with the value three. In other words, five was repeated three times. And yeah, believe it or not, this is the direct initialization of the node. Now let's initialize the tree itself. It's not def, it's again tree is a class. So treat the class BST. And I think it is better to wrap it in some of its own class. Let's wrap it in first. Yes, and yeah, again for a tree will have only one initialization, and yeah, for tree to create a tree, you know, don't need any data and all. We will have only one value again. So I'll tell that it will just be the root of the tree. Yeah, and self root is actually DT sort of not the MRO. I don't know why that thing. Yes, and initially the root will have nothing. So let us call it none. And yes, so now after doing BSC, there is only one thing to do, and which is insert. So self, and you will get the value which is to be inserted. And now what you have to do, just think about it once. Enough thinking. So what you can do, first you have to keep track of the root itself or the current pointer to the root. So let's call it curve self dot root. And what you have to do, again think about it. If actually there is no curve dot data, what does that mean? That means you are actually initializing the root itself. It's not cut again, it's curve. So there is no curve or data. That means there is nothing that there is no tree itself. So now directly initialize the tree. It's actually a new node object containing the data value. Again, it is a BST sort dot node object mainly because the node object is actually present in the BST class, and to refer to it, rather we have to use the BST sort. And after doing that, you can directly return. And the one thing to note is that the return type of insert is actually none. Yeah, you can directly write none also. This means that since Python does not have strict enforcing of return types and all, we can directly explicitly mention that this is supposed to return none. But yeah, this is to be done in big applications and all for these kind of algorithms. Let's not do that. Else, what you have to do while curve exists, and now yeah, this is just like a binary search if you know about that. So but with very minor modification. So if curve dot data becomes equal to the value itself, that means it is actually a repeated value. And I again told you what you have to do to that. Do it if the value is actually repeated. So you take the curve and then increment the node count by one. Else what you will do, if the curve dot left exists, that means there is a node on the left. And if there is a node on the left, go to the left node. But if there is no node on the left, what does that mean? That means you have reached the end of the tree. And on reaching the end of the tree, there is only one thing which you have to do. And yeah, before doing that, what you have to do is that first check for the value itself. I forgot about that. If the curve dot data, if it is greater than the actual value you're checking on, let's since we are actually comparing with value, so let's see value first. So if value is less than the curve dot data, so what does that mean? That means the data is greater than the value itself. That means that you have to go to the left node. Just like in binary search, what you did, if the middle was greater than the if the middle was greater than the target, I am getting confused again. If the middle was greater than target, then you have to go to left, and if the middle was smaller than the target, you have to go. No. If the middle was greater than smaller than the target, you have to go to left, and if the middle was greater than the target, you have to go to right. Right? Yeah, it might be one of those things. Again, like I'm a bit confused over here. If I write it out once, I'll remember it. But this basically works on the same fact that when the value is greater than the data, that means the current node data is bigger than the value itself. So you have to go to the left. So, but again, before, yeah, this is it. But you can again I want to tell that you can't directly go to left again. And again I'm making lots of mistakes. Or it's not else. It's not else because there is one more condition to check. So else if the value which you're going to check is actually greater than the node dot data or the current dot data, what you have to do? You have to go left. But when can you go left? Only if the current left exists. So if curve dot left exists, that means you can actually go left. And if curve dot left does not exist, that means that you have already reached the least node. So you have to create a new node. So else what you have to do? Curve dot left is actually a new node. So BSR dot node, not BSC, node with the data of value. Else what you have to do again is okay. Uh, let's not look at that now. So else what you have to do? The else condition tells that the value is actually greater than the curve dot data, and if the value is greater than the curve dot data, then you have to go to, yeah, just think about it. Yeah, I'm thinking again. Since you are going left on the above part, it is pretty obvious that you have to go to right. So else what you have to do? If the again the same thing, if curve dot right exists, that means you can still go to right. So curve is curve dot right, or else what you have to do? Curve dot right is actually a new tree node or node with value. Again, it's not just node; it is BST for BST. It's actually BST for dot node. And after the one more thing to know, after putting the new node, that means you are finished. Directly return. Again, after doing this return, and again after doing this directly return because retur, yeah. And this is basically it. This is how you create retrieve node and insert it. And yeah, again remember the special property. Again I'll tell. Just keep it in your mind. The in-order traversal of a binary search tree always gives you the answer in sorted form. So now what you can do is directly do an in-order traversal. Again, there is no need to take any values for this because you can actually access the self dot tutorial. Self dot root can be accessed, and let's call it curve is self dot root. And again, you have to have a stack to do in-order traversal. And while stack exists or the current root exists, what you have to do? While the current exists, but before going to left, append the cur value, and uh, again the cur value is actually the top of the stack, and now go to the right. So cur is actually cur dot, and yeah, this is how to do in order traversal, and let us return the answer over here, and we have not declared the answer array. So what you have to do? Actually, again, again, if you remember, you are actually keeping track of the node count also for repeated values. So count is actually cur dot node count. Yes, and while the count is greater than zero, what you have to do? And answer dot append the current root dot data, and then decrement count by one. I hope you understood why we are doing this. Just think about it once. If the count is greater than one, that means we had two elements, so we have to add all the elements, right? So let's create. Yeah, everything is done. So let's create an object of our class. So get is sort dot. It's actually of type BFT. So BFT dot insert. Let's do a thing for I 1 to 10. Directly let's insert I over here, and directly let's print the BFT dot in order. Directly print the BFT dot in order. Let's write out one. And as you see, the values are actually sorted. And let's do okay. And let us do some random numbers. Why do like this? So import random. Uh, Random dot random from 1 to let's do 1 10,000. And as you see, again you're getting sorted values. And yeah, what let's do. And the now the only edge test case left is that checking on what happens if you have more than two same values. So now again let's insert I, and let's do the same again. But rather than going from 1 to 10, let's go from 5 to 10. And as you see, 5 is repeated 2 times, 6 is repeated 2 times, 5 is repeated 2 times, 8 is repeated 2 times, and 9 is repeated 2 times. And yeah, that's how this is one more way to solve. I hope you understood. Let's just go wacky and do 100 elements. And yeah, again, as you see, every element is sorted. Yeah, you can go through it once. And yeah, that's about it. That's how you implement a BSC solve. And yeah, it basically works like binary search. So again, in binary search, what we did, first we calculated the mid value. And if the mid value was actually greater than the target, then what you did, just think about it once. So if imagine you had an array of, let's write an array, come 2, come 3, come 4, come 5, come 6, 9, yeah, and your target was actually, let's tell target was 7. So you calculated the mid, and yeah, no, let's tell the target was 3, and you calculated the mid. Mid is actually greater than the target, so you have to move left. And yeah, if the target was 8, then mid is actually smaller than the target, so you have to move right. So this also works in the same way. While inserting, what you do, you check if the current value is equal to the current data is equal to the data. That means that if it is equal, then just increment that count by one. Or else what you do, if the value you want to insert, if it is greater than the current dot data, it means that you have to go to the left part. And if the value you want to insert is less than the current dot data, that means you have to go to the left part. I think I stumbled again. If the value which you want to insert is smaller than the data of the current node, then go to the left. And if there is no node, then create a new node. And if the value which you want to insert is actually greater than the node, then go to the right node and then insert over there. Because yeah, I hope you yeah. I blabbered on about so much, but I did not explain what a binary search tree is. Binary search tree is a specific form of a tree in which what happens is the root value or the root will always be greater than all the left children and smaller than all the right children. So yeah, to maintain that property, we are inserting it like this. And yeah, that's basically it. I hope you enjoyed it. Yeah, thank you. Stay sharp and grind more DSA. You can do it.